All right. It's my pleasure to introduce Professor Chenyang XU from Princeton University to begin our afternoon session. And the title is Finite Generation for Valuations Beyond Divisors.
Okay, thank you very much. So first, I want to thank the organizers to give me the chance to speak in this great conference, for this conference in honor of Tian. So actually, I'm an algebraic geometer, so my talk is mostly about algebraic geometry, but I understand that here not everyone is an algebraic geometer, so I will try to make my talk accessible to more general audience. So basically the behind the story of this is basically a tales of two series. So in the late 70s, I think we all know Yao's work on Calabi-Yau conjecture made the canonical metrics a central topic in computer geometry. But slightly later, but roughly the same time, Mori initiated the mirror model program, which revolutionized like a higher dimensional geometry. Then in 1980s to 2000, in the next 3 decades, I mean, both series have a spectacular progress. So here I outline 3. I mean, one is Tian's work on the Canonical metric on final varieties. Next is, the proof of finite generation of pre-canonical ring, led by Hickman-McKernan in early 2000, and also then the moduli of higher dimensional varieties, led by Kola. So, these are all my mathematical heroes. Of course, there are other progress as well. I choose these 3 because they are very related to my story today. And the main theme of the story is in the last decade, these 2 series actually intersect and produce like a very striking result to both sides. So I will first talk about the analytic side, although my results will be mostly still algebraic. So, I think I don't need to say too much about this, but let me just introduce that X is a complex manifold. The Cayley-Einstein problem for the final case is to find the metric omega such that the reach omega is equal to omega. And of course, we know that the left-hand side of the class is the Chen class, first Chen class of the complex manifold. So that means this first Chen class has to be positive in the algebraic sense. So the class should be ample. Then, 1997, Tian made this very insightful conjecture that this existence of Cayley-Einstein metric, which is a purely analytical condition on final variety, is actually equivalent to a notion called K-stability. And later, Donaldson made this notion to be algebraic. So here, I want to outline how the analytics people think about this question in a very basic level, because that's what I'm trying to draw analogy in the algebraic geometry setting as well. So basically, we consider this space of all smooth metrics, smooth functions, which is the space of Kähler metrics with the same class, and we define some functional, and basically, this functional is chosen in a way such that if you have a solution of this complex monotone equation, which is equivalent to have a Cayley-Einstein metric, if and only if, you can find the critical point on this space for this function. But of course, this function of space of smooth function is not complete. And if we want to do analysis, we have to take a completion. Depend on different analytical theory, you might take a different completion. It might, that will completely change the story. But here, I'm not going to add any details because that's not what I'm going to focus. But anyway, you want to take a completion, show this functional actually can be nicely, basically continuously extended to this complete space, and then show that if a minimizer exists, then this minimizer is actually I mean, first, you can easily find this minimizer in H bar because it's a complete space, I mean, under some right condition. I mean, for instance, we know in the final case, it's not always true that there is a minimizer, but then under some right condition, you find this minimizer, and then you have to show that this minimizer, which a priori only exists in H bar, is indeed in H. So we want to draw algebraic analogy of this process. So, but let me just first outline what makes this like a recent progress on this theory possible. So, I mean, our goal is to understand this K-stability, which is the algebraic notion, but we really want to develop a theory around this, understand it using our way, and possibly apply it to some important questions in algebraic geometry. So historically, I mean, people study K-stability, this kind of notion, through the lens of the geometric invariant theory of Mumford. I mean, there's a reason for people doing that, because it's from some perspective, it really looks like a geometric invariant theory. However, one of the main observations in the last decade was, turns out people realized that it turns out the minimum model program is actually the right algebraic framework. So somehow we have to think about this question, use it through the lens of minimum program, and here we can get a stronger result. And roughly speaking, the reason is that in this question, there are many hidden finite generation properties which you have to prove. I mean, there's a very deep statement which you have to spend a lot of energy to prove it. And so far, the best tools in algebraic geometry to prove finite generation is using minimum program. So somehow, if you don't say those finite generation results, then it's very hard to make your theory forward. I think that's one of the reasons why we use minimum program to get the stronger results. And I mean, the basically finite generation shows up in our understanding of K-stability everywhere, but the most deep application is that it plays a role similar to regularity theory in analytic geometry. So, in other words, as you will see that somehow, a priori, you might just find something which lives in a larger space, which is not the algebraic object you want to, I mean, which doesn't have the algebraic property you want to have. And to establish those properties, you have to prove certain finite generation results. It's like you start with a weak solution, then you prove it's smooth. So, but the one major advantage for algebraic theory is it works in a singular space very well. I mean, you heard in Jensong's talk this morning, when you try to extend the result from smooth case to singular case, the analytical result, you have to work a lot. Here, there is no difference. I mean, all the proof, if we work for the smooth case, then it works for the singular case. So I mean, this slide is for algebraic geometry. I mean, if you don't really know this notion too much, it's fine. Basically, that just say we can define some function. Okay, you will say this in the next page, but let me first state what I wrote on this slide, that we define two functional on any divisor E over X. Here, E is not a divisor necessarily on X, but it could be on some bidirectional model. So you might have first a resolve and your model such as the E is on Y. And you define this log discrepancy of divisor, which, I mean, is this way. Basically, it's a multiplicity on the Jacobian plus and plus 1. So if all these numbers are positive, if and only if the singularity is called the Karmata log terminal, KLT. Actually, it already appeared in Jensong's talk. So if you understand his talk, you should understand this one. So the next quantity, I mean, the first quantity appeared in minimum program all the time. So once you say this kind of quantity, you immediately should realize that this must be something related to minimal program. I mean, the second one is actually less, as far as I can say, before it was, I mean, it appeared in some context, but it was less popular for people to study. So basically, it's so-called the expected vanishing order. So along this E. I mean, I'm not going to explain this too much. I mean, this is the formula. And the crucial thing is in 2015, Fujita and Lee, they proved that the K-stability, which were originally, I mean, in Tian's definition, is defined for one parameter subgroup degeneration of your X. So you consider all such kind of degeneration. But here there is an equivalent way to characterize those notions by just consider A and S. So if it's K semi-stable, if and only if A is always less, greater or equal to S, and K stable if A is larger than S, and the uniformly K stable if A is larger than 1 plus epsilon S. Here epsilon doesn't depend on E. That's a crucial point. So there is a uniform epsilon such that the A is larger than 1 plus epsilon S. So in 2015, I mean, Fujita and Lee built on earlier people's work, finding this characterization. Then, I mean, the main reason I introduced this, now I can set up this function A over S. So it's defined over all the divisor E over X. And we just define delta X to be the infimum of this A over S. And the previous slides, this Fujita-Lee criterion just say that X is K semi-stable if and only if the delta X is larger or equal to 1. And the uniform K stable if and only if delta X is larger than 1. And the K stable, a priori, there is some mysterious thing because A larger than S doesn't necessarily mean the infimum is larger than 1. I mean, the infimum could be 1, although we prove that's not going to happen. So basically, later, I think in the work of Rubinstein, Cherasov, Zhang, and also Berman, Buxton, Janssen, they actually show that this delta, which was first defined in this algebraically, is actually equal to the something like the maximum reach lower bound. So there is an analytical interpretation of this quantity as well. And I think this quantity probably first appeared in some Tian's work. But as I said, if we want to draw the analogy to the solving this PDE, then we have to look at the space of this function A over S. We know it's defined over E, over all the divisor valuation. But the divisor valuation is not a good space. So the way you should think about it is it's like at least it's like a rational numbers. So somehow you really want to extend this to some like a complete space. And we found the right complete space. I mean, there are different perspectives. For instance, there are some people think about this kind of completion of the space to be something like all the space of non-Archimedes metrics. Here, from a more algebraic geometry viewpoint, we take the completion of the space to be the space of valuations. So this is a natural space attached to X. I mean, this is some space studied by Zariski, I mean, like a long time ago. So the definition is rather easy. But the crucial thing we prove, together with Yuchen Liu and Ziquan Zhuang, is that if I assume delta is less than n plus 1 over n, n is the dimension. So remember, if n is larger than 1, that's uniform K stable. So we don't have too much to say about that. We already understand it very well. So we have this slightly technical condition that is less than n plus 1 over n, but it covers all the cases we are interested in. So then, actually, the delta is computed by a divisor. So originally, I mean, it's an infimum, but then once you extend this function to a space of valuations, it's not very hard to prove that there is a valuation reach the minimum. But you want to show that this minimum is actually indeed reached by some divisor itself. It's not just some abstract valuation. So that's the content of their theorem. So usually it's over X. Usually it's over X. So intuitively, this means that if X is really below 1, the delta X, then in that case, there is an optimal discretization. So this X, indeed, among all the test configurations, there is a 1, which minimizes the photonic invariant if you normalize it correctly. So I think this type of question, of course, is closely related to modular problem, which I'm going to explain later. But the two consequences of this statement is, the first is K-stability is same as uniform K-stability. The original K-stability just say A is larger than S. But because we know delta, the infimum is computed by A over S, then actually, if A is always larger than S, then it has to be uniform K-stable. So the delta is actually larger than 1. I mean, this is important in the theory, in solving the Yao-Tian conjecture is for the singular Fano case, using this kind of like a proof potential theory, without by Berman, Buxon, Janssen, and also Li Tian Wang, they already proved that the right-hand side implies the existence of unique Klein-Stein metric, even in a singular case. So I mean, as we know, the original solution of the YTD in the smooth case, I mean, is only for the smooth case. If you want to extend it to a singular case, I mean, the analytic theory goes to so far, only goes to the range that you have to assume the algebraic side, you have to assume the uniform case stability condition. But however, you can now use algebraic geometry to prove that K-stable is the same as uniform K-stable. So actually, this goes back to the original version of Yao-Tian Donaldson. And to algebraic geometers, what's more important, I mean, at least to us, is this implies that the modular space of K polystable Fano variety is compact. So in other words, they just say that the varieties with, I mean, the space of Fano varieties with Klein-Stein metric is actually compact. So in the smooth case, I mean, of course, this was proved using this kind of Tian-Caesar partial estimate type thing. But in the single case, again, there was no such analytic theory available, at least now. But in the algebraic geometry level, we can just prove it completely algebraically. So, I mean, I want to very quickly go through the proof. I mean, by just giving some like a general idea. But roughly, you can divide this into 2 steps. So the first step was actually done earlier by joint work with Blumen and Liu. So we show that when you take the infimum, you actually, originally you have to take among all the divisor E. But indeed, you can just take E comes from a sequence of blow-up for fixed log smooth model. So I can assume there is a log resolution Y of X, and all the E I care is just coming from the blow-up of the strata of this YE. Of course, there might be infinite blow-up. So if you start with like playing with two lie, you can just blow up and then continue to blow up. But again, you know something very bounded that they come from the blow up of one model. And prove this, basically there are also 2 steps. You first prove that this, instead of proving that there is a unique YE, you can just prove there is a bounded family of YE. And that actually requires this so-called abundance of complements proved in Burka. So I mean, when Burka proved the BAB conjecture for Fano varieties, I mean, he simultaneously proved some other deep boundings for Fano varieties. And this is actually the one we need. And from abundance family to one family, we need some version of universal log progenoa, which was proved by Haken and McKernan a while ago. But there is still an issue. This doesn't solve the problem because apply this EI, you might need to go higher and higher blow up. So if you just regard them as a divisor, it's not clear, I mean, what you should do. But however, if you regard them as a valuation, then they all live in a fixed dual complex. And when you compute the minimizer, you can actually rescale each divisor. So in other words, you have a fixed CW complex. Each EI gives you a point. And of course, you can just take the limit of this point. So that limit of the point is give you some valuation called, I call it V infinity. And you can show that this V infinity, this will minimize your delta. So if you take A and over S on this valuation, that's going to be equal to delta X. However, there is still a problem because this V should be V infinity, could have irrational coordinates. So only those rational coordinates correspond to a divisor. So somehow you have to show that it's not, you can always find a rational solution to this. And the way we do is that we have to show the associated gradient ring of this G of V infinity is fine generated. And once you know that, then it was known that any small rational perturbation will satisfy that delta is equal to A over S. So the crucial is to show that this is a fine generated. Sorry, R here is just a coordinate ring. So it's a ring of all the section of H0 minus MKX for M from 1 to infinity. So you have to show this ring is fine generated. So, and that's what we show. Actually, we have two proofs. I mean, the second proof is stronger than the first, and which can also be used to prove the local case. But let me just give you some remarks. So if the V infinity is a divisor, this just follows from the classical type of fine generation, like the one proved in Berka, Kashini, Hickey-McKernan. But if V infinity is not divisor, if it really have irrational coordinates, then this is really beyond the classical case. So you have to really extend some of the fine generation, this kind of minimal mode program theory to do this. I would say this is one of the most difficult steps in this entire program. And one of the difficulties is, the right element is not the minimizer satisfying generation problem. It should be two steps. Is the minimizer satisfies some biaxial geometry condition, and this biaxial geometry condition implies the finite generation. So you have to find, and then the mysterious thing is to find what's the right biaxial geometry condition. And actually, the condition we found differs with the classical one. So we actually realized, actually it was the first example by Aban and Zhuang. They realized that the same condition which imply the fine generation in the classical case doesn't imply the fine generation in this new case. You have to find a more delicate condition to imply this fine generation. And that's what we actually work, quite a bit to find it out. So, but this package works in many other problems. So I took one example that if we start a Kähler-Rich soliton, then that just imply that for any final variety, there exists a unique Kähler-Rich soliton degeneration. So of course, if the smooth one, again, this was conjectured by Hamilton Tian and solved by Zhang, sorry, it should be Tian Zhang, and Baumler and Cheng Wang. But in their solution, they need the X to be smooth. And again, we don't need a smooth anymore. We just need for any final variety, this work. And the way to solve this type of problem is just exactly parallel to what I was saying. First, you find the functional, this time now it's called the H functional, and which that was found by Han and Li in the earlier paper. And they want to show that there exists a unique valuation minimizing this function. And then we just show again this functional satisfies some finite generation property. And then if you take the approach of that, this gives you the K semi-stable object degeneration. And then you work a little bit harder, to use our finite generation again to show that this K semi-stable object actually has a Kähler-Rich soliton degeneration. So basically, the degeneration from any final variety to a Kähler-Rich soliton, this is a purely algebraic picture. Of course, the original one was carried out using metric, but if you are not interested in metric, you're only interested in the underlying space, then there's a purely individual picture behind this. So in the last maybe, let's say, 5 minutes, sorry, I want to talk a little bit about why our algebra geometers are very thankful to Tian's insight to Fano varieties. That's basically the module of varieties. So of course, the module of varieties, this is a central problem in algebra geometry. If you study the elliptic curve, that goes back to Albert, Jacobi, and Riemann, Weierstrass. In higher dimension, go to Teichmüller. But I mean, the question is, I just want to find a class of variety, and I want to construct some space to penetrate it. And the very first successful algebraic geometry theory is by Mumford to use GIT to construct moduli space for curves for genus larger than 2, larger or equal to 2. And later, if you allow certain singularities, Deligne and Mumford found this compactification. I mean, this play a central role in modern algebraic geometry. And now we want to generalize this to higher dimension. And Kohler, Schiffer, Baron in like basically about 40 years ago, they proposed the right stability for higher dimension. Under the case, the chain class is negative. So in other words, the Kx is positive. And this basically intertwines with the development of a minimum program. So I don't have time to explain this too much. But let's say, now come back to our theme. We want to study module of Fano variety. So before 2010, basically very few algebraic geometers think this is possible. Because if you look at the existing theory, I mean, all the Fano variety, if you put all the Fano variety into any existing theory, it's just there are just too many pathological examples. So for instance, if you want to use GIT, there is no natural extrinsic theory. If you want to just use the minimum program, then again, there is too many pathological examples. But of course, the solution is we want to consider all Fano varieties, but now we stratify it. We're only in the semi-stable one, which is the open part of this space, indeed yields a good moduli space. So somehow this K-semi-stability plays a very, very deep role in our understanding of modular Fano varieties. So this is a little bit like the analogy of vector bundles. I mean, vector bundles, you don't study modular of all vector bundles. You only study modular of the stable one. And here, Fano is that. You have to post some extra subtle condition to make the modular theory work. And that was Tian's K-stability condition. And so this is statement of the K-moduli. I mean, I think for different geometers, if you are interested in basically the point-wise thing, then basically it's this modular space, which is a space that every point precisely corresponds to a Kalenstein-Fano variety, which is interesting to you. But for algebraic geometers, since we're also interested in family, so we actually look at the stacks above it. And we construct this modular space as a good modular space of this stack. And as I said, the most deep, the deepest property of this modular space is it's compact. So that basically was what I stated before, that all K polystable Fano varieties, they form a compact set. And another thing is it's actually not just, so if it's compact, I just say it's a pauper, but you want to make it to be actually projective, and then you still have to find an ample lie bundle on that. And that's the same lie bundle. And again, I think the first person who realized the same lie bundle might be positive on this modular space was Tian. But this was proved much later, I think 5 years ago by Ziquan Zhuang and myself. So I mean, many people make contributions to this theory. I just write down some names. I mean, there is not enough space to put all the names. So I have 1 minute left. So let me just say, this actually new construction of space incorporated many traditional study of modular varieties into this new territory. So for instance, people study word crossing, study many property. For instance, there are many problems people study in the case B case. Now you can also study in this case. And also a very active research field is to find many explicit examples of K moduli. I mean, we prove all this like general properties, but algebraic geometry is kind of example-oriented subject. So you actually really want to write down many examples and to understand what this precisely parameterize. And this is a very ongoing subject. And the last thing is that the stratification of this stack of all finite varieties is still be a little bit mysterious. So somehow I think people should work a bit more to understand what this stratification means. I mean, we understand the semi-stable part, that gives you good modular space, but what about the other strata? Like whether there is a good parameterizing theory for other strata. I mean, in the vector bundle case, we know, but in this case, it's still not completely clear. Okay, thank you very much.
Thank you, Chenyang. Any questions or comments? Oh, yes.
You mentioned that the stratification was mysterious. Many moduli spaces have stratifications. For example, the space of Riemannian metrics on a compact manifold is naturally stratified by the group of diffeomorphisms. If there were some way to structure this so that your moduli space was a quotient group, the symmetries of each one would lead to a stratification, which could account partially for the stratifications that you're seeing.
I mean, the prototype theory, in my mind, was, if you study the module of vector bundles, then the unstable one, I mean, a priori, it was not in the modular theory. However, if you fix the Hadana-Shimohan type, then this part actually is isomorphic to some like product of modular space of stable bundle. And then any vector bundle, because there exists a unique Hadana-Shimohan filtration, actually the stack of unstable bundle with a fixed type has a modular map to this, like a kind of like co-modular space. And then the fibers have some kind of something like a non-reductive GIT structure. So that's the kind of picture I would like to see whether it holds in the final case. But I would say this is still far away. Yeah. So.
You just mentioned something about the moduli space, like the K-semi-stable part. That's like open.
Yeah, that's open.
Zariski open.
Zariski open. Yeah,
that's another theorem.
That's proved by Bloom and Liu and myself. That's okay. Actually the first step. I talk about in this like regularization problem. One consequence of this is the K-semi-stable is Zariski open. Actually, there is a second proof, but it's along the same kind of idea. The second proof, but using different environments.
And then for the soliton case, there's like a version of delta that's.
Yeah, that's an edge function now. I mean, I think invented by.
So it's not like a variant of delta. It's something else.
It's kind of like delta is A over S. The edge is A minus some weighted S. Mm. So this weight is weighted by some exponential function. So then, I mean, I think that was probably inspired by some work by Tian Zhu and maybe some other people. I mean, too, and then they wrote down this algebraic version. And so it has some similarity with A minus S, but you have to do the weighted S.
So related question. So for this optimal destabilization, this gives you the vector field for the model for the soliton, I guess.
Yeah, exactly. I mean, well, in this one, the optimal, I mean, there are two steps. So the first just give you the model to the semi-stable one. Mm-hmm. And then you have to further degenerate the semi-stable to polystable one.
Double degeneration.
Yeah, the polystable one has a soliton. I mean, we can prove that.
And suppose you have tens partial C0 for the singular case. Would it help? Would it give you some shortcut?
I think that's a question for you. I mean, I don't know much actually
I see.
about, yeah.
Okay. Any other questions? And
Okay, maybe I ask us questions. So in this evaluative criteria, so I guess you use the resolution to define AXE and SXE. Is that, I guess it's also possible to define it more intrinsically without using a resolution, right? For example, SXE is just the integral of it's just a bunch of volumes. And the volume you can think that TE in some sense like vanishing of things. At least for T to be some rational numbers. So also for XE, is that possible to instead of using a divisor, just purely intrinsic on the original X? So this might give you some property of X if it's k-stable. Like E could be instead of divisor, if you don't use a resolution, it's just subvarieties or even points. You can associate some length to that, which correspond to multiplicities.
Yeah, I mean, okay, I think you can, I mean, for S, for instance, you can actually work on X instead of on the resolution. But you have to, there is something you have to pay. It's, if you work on X, usually it's not a single subvariety, it's a sequence of subvarieties. So there is a asymptotic process there. So you have to, I mean, you know, for multiplicities, I mean, of course, there is also, when you compute the multiplicity of a subscheme, there is also a asymptotic process. But here, I think even the subvariety you look at on X, I mean, there is actually a natural one attached to it, but it's not one single variety. It's a sequence of ideal. And that if you work with this like an infinite sequence of ideals, then that is really on X, and then you can define the S there. For A, actually, I'm really not sure. I mean, the log discrepancy, so far, I mean, we studied this for 5 decades. I think all the definition I say is you have to go to a resolution. But for S, you are right, you can compute on X, but the price you pay is it's not just one single variety, it's a sequence.
Yeah, but so I guess it's for S, I guess you say once you find this optimal one, I guess that's probably it may involve a few devices, but not necessarily infinite. But for AXE, I understand that this is you know, it depends on how you define it. You have many resolutions. On each resolution, you might have multiplicity, so relative canonical line bundle. But on the X itself, maybe you need to define this. I mean, of course, the easy way to define this, you want to take all the resolutions and take kind of a minimizing or something like that, and to define it on the X. So I still think maybe there's a way to define that, and whether that can be attended in a finite fashion could be also interesting. I believe in the end, it must be attended by, I mean, it's just in the finite fashion because it's an algebraic problem. So it's yeah, I don't know. I just think it'd be nice to have an intrinsic characterization on the origin X. It's also indicate that the X itself has some properties, intrinsic properties.
Okay, I see what, I think the one which minimize this A over S, those are finite generated. So for those S, you can really compute on X in the finite level. So in general, I mean, those which minimize it, then you can compute this on X. And in general, you have considered this like an infinite one. Of course, you can approximate the infinite one by finite one. And then that's exactly the problem that you want to show that the one minimized is finite generator. So those one, when you use a finite generator to approximate, it doesn't lose any information, and that's what we show. So if you assume our result, I think it's reasonable to say it's okay to just work in the finite level now.
No, I understand that we just assume your result, assume finite generated, and
that's right.
just it just kind of try to find a different kind of interpretation and which may be some geometric implications. Another thing is I guess you always assume a fellow for other polarization like a K and ample line bundle plus KX or things like that. It's air ample line bundle is very ample in that case. Is there something similar to this? I guess Chili yesterday gave a talk. He has some also uniform stability things, and is something one can extend.
My feeling is the kind of non-commuting theory, I mean, one can general to the general polarization case as in Chili's talk. However, this kind of minimizing thing, I mean, this kind of finite generation, for instance, I can say that I think so far there is no real deep finite generation result proved for any kind of deep finite generation result proved in the constant scale curvature problem. So somehow so far I don't see how to like use minimum program or use any finite generation to attack this kind of like a general polarization. And that's a big mystery to me. I mean, somehow this finite generation, which is really deep, I mean, the final case, so far we don't know what is the right statement in the general polarization case. I mean, if once we start to say there are some like finite generation type result in the general polarization case, then I would say there might be a more algebraic geometers can prove in that case. But so far, I don't think we have seen any result like that.
I guess in terms of this minimum model program, or this what I was doing with Song Jian, these analytical things. So probably you don't need that general constant scalar geometrics anyway, because everything can be reduced, deformed to canonical ones, even sometimes need to be twisted. So maybe that's instead of studying, for example, one is not a canonical polarized, but it can be twisted, or it's on a fibration case. So kick out of this Calabi fiber spaces, that's fibers, and then reduce the moduli to study on the base with a twisted stability. Maybe that's also a way to see that. But anyway,
Yeah,
I just
I agree.
No.
Okay, so the question about the component number of module space.
I mean, I think there is no general theory for that. I mean, we know there are the finite many components when you fix the volume and so that comes from the boundaries. But in general, we don't know. I mean, so far, I think the kind of examples people look at is usually up to dimension 3. At 3, I mean, basically there is a classification theory about smooth final threefold. And I think there is something like a 105 family, out of them 70 something, the general number has color symmetry. And then you try to study all, like the question, like whether all of them have color symmetric. And I mean, for instance, we know in V22 that's not the case, but what is the right, like compactification of that in the single case? So this is a kind of question. So we don't have a good general result, like bound the number of components, like what kind of singularity appear on the wall. No, we don't have those.
So one more for toric case, right? So you cannot do deformation. Since toric structure is not preserved, right?
Well,
so what's the difference in your module space?
I mean, in toric case, in toric case, if you are case stable, you can deform it, but not as toric variety.
Yes.
So and then there are many like a moduli of final variety which contain one member as toric, but other members are not just toric anymore. because it's not a toric deformation. Yeah, I mean, in 3-dimensional, we already see those examples a lot.
So I mean, in general, for you, modular space Chenyang does not help to classify such a symmetry quantum manifold, right?
I thought they are all stable. You always have soliton or Einstein.
Well, I mean, yeah, that's stable as a soliton. I mean, I think if it's just stable as a fundament itself, I think there is no probably. I mean, you know, people try to classify the 4-dimensional toric Fano variety, and there might be, I don't know what's the scale, maybe 1 million examples. Actually, I don't exactly know scale. I just made up this number. So I don't know how many like toric of them among them are k-stable. Maybe like some, let's say 20% or something like that. So I mean, you can look at those examples, but yeah, I don't.
Okay, thank you.
Any other comments or questions? Well, if not, let's thank Chenyang again for the wonderful talk.